In this video, we're going to review the circle, and in particular the unit circle definitions of our trig functions. So far, we've looked at the definitions that were the right triangle definitions. And those are a little bit limited, because in order to use the right triangle definition, your input has to be an acute angle. It has to be in radians between 0 and pi over 2, or in degrees between 0 and 90 degrees. But trig functions are actually defined for almost every angle, and we'll see that if we switch to using the circle definitions. Now, we're still talking about sines and cosines and tangents. These new definitions are going to agree with the right triangle definitions if our input coincides with an acute angle. But they're larger definitions. They allow for a larger domain so that we can input to sine and cosine any angle that we want to, and to the remaining four trig functions, almost any angle. So let's see how that works. Now, there are the circle definitions, and that would be for an arbitrary circle of radius r. Now, I've drawn a circle here centered at the origin with radius r. By definition, the radius of a circle is a positive number, so r can never be negative. I've drawn that here on the xy plane. Let me just show you a notational convention that I'm using. I've called this the capital x-axis and the capital y-axis. That's because sometimes we call the input to the trig functions little x. And I don't want to confuse the input, which I'm thinking of right now as an angle, with the x value here. So when I'm referring to the xy plane, it's the capital XY plane. To avoid confusion in this video, I'm actually going to call the angles theta, but often you'll see the input angle being called x, and that's perfectly acceptable. It's different from this capital X. Okay. The unit circle, of course, is just the circle centered at the origin where the radius happens to be 1. So when we look at the unit circle definitions of our trig functions, that's just a special case of the circle definitions. Okay. So I'm going to start with sine of theta. So I've got this table up here. We're going to go through the trig functions, remind ourselves of the right triangle definitions, and I'm going to show you how we can use that to get the circle definitions. Okay, so over here, I've basically got an acute angle theta in standard position right there. Okay, and you'll notice that's going to intersect the circle at some point x, comma, y. Okay. Now, if I drop a perpendicular here to the x-axis, I've just created a right triangle. This side would be x, because we're coming over x and up y, so then this side, of course, is capital Y, and the hypotenuse is r. Okay. Now, if I'm in quadrant 1, if theta is an acute angle, x and y are both positive numbers, so they are legitimate side lengths. Okay. If I'm in any other quadrant, at least one of x or y is a negative number. I could view them as signed side lengths, but they wouldn't be actual length. But in quadrant 1, these are actual side lengths. Okay. Now, the right triangle definition for sine of theta is that it's the opposite over the hypotenuse. What I'm going to do is apply that to this right triangle definition using x, y, and r. So the opposite side is y, the hypotenuse is r. We get capital Y over r. Now, if I forget where that came from, that y and r were side lengths, okay, I can say for any angle, no matter what angle I wanted to work with, if I drew an angle like so, that's going to intersect the unit circle at some point x, y. Now, I could, if I wanted to, draw a triangle. The signed side lengths would be x, y, and r. R would be positive, but this angle happens to be in quadrant 3, so x and y would be negative. But I can just take this ratio of the y value where we intersect the circle divided by the radius of the circle. That is the definition of sine of theta, and that works for any angle. So the angle that I drew here would simply have a negative sign because the y value would be negative, but r is always a length. It's always the radius of the circle, so it's always positive. Okay, so what's kind of nice is I can use my SOHCAHTOA, my right triangle definitions, to remind me of the circle definitions and to see the connection between them. So I don't have to feel like, oh man, I've got these two different things that I have to know. It's just different ways of looking at things. Okay. If I'm on the unit circle, I can do exactly the same thing. I can drop a perpendicular. The side lengths are x and y. The radius now is 1. So I would get y over 1, or just capital Y. So the unit circle definition is that it's just the y value where we intersect the unit circle. If I'm working with a bigger circle, I have to look at the ratio of that y value divided by r. Pretty cool. Okay, so with cosine of theta, okay, I'm going to do the same thing. It would be adjacent over hypotenuse. Let's write that in as the triangle definition. But that becomes x over r. And on the unit circle, that becomes capital X over 1, which is just x. Which means, and you'll sometimes see it this way, this point, capital X comma capital Y, can also be labeled cosine theta, sine theta. The x value is the cosine, the y value is the sine. Now, that only works on the unit circle. If I'm on a larger circle, the x value would be r times sine of theta, and the y value would be r times sine theta. Okay, let's see. Let me erase what I just wrote because it's taking up my space. So tangent of theta is opposite over adjacent. I can see that becomes y over x, y over x. That doesn't change because there's no r in that definition. For the three reciprocal functions, I want to be a little bit careful, and I'll show you why. We actually won't see why we need to be careful until we hit cotangent. But cosecant of theta, I can think of that as either the reciprocal of sine theta, or if I take the reciprocal here, that would be hypotenuse over opposite. So, on a circle of radius r, that's r over y. And that's exactly what I get if I flip this fraction. And on the unit circle, that's 1 over y. Okay, let me just point out, with sine and cosine, all of these things are ratios. They all are fractions, because they all come from SOHCAHTOA. Even these, which are capital Y and capital X, start out as this ratio, y over 1 or x over 1. Okay. But with sine and cosine, what's in the denominator is the radius of the circle. So r if it's a generic circle, 1 if it's the unit circle. That's never 0. As soon as we hit tangent, tangent has x's in the denominator. Cosecant, I can see, has y's in the denominator. These functions are going to be undefined at any point where whatever variable is in the denominator would be 0. Okay. So there will be some restrictions on the domain for all of the trig functions other than sine and cosine. All right, if I look at secant of theta, I usually think of that as the reciprocal of cosine, but I could also say that's the hypotenuse over the adjacent. Either way, that's going to become r over x, or on the unit circle, 1 over capital X. I'm going to draw in some lines here because I'm starting to get crowded. Okay, cotangent is the one that I need to be careful of. Because for the right triangle definitions, I can think of that as the reciprocal of tangent. But I don't want to just think of it that way here. Most of the time, it is the reciprocal of tangent. But I can see tangent would be undefined if x is equal to 0. But if I flip this formula, I get x over y. That's defined if x is equal to 0. So rather than thinking of cotangent as being the reciprocal of tangent, which is true for the right triangle definition, I'm going to think of it as adjacent over opposite. Okay. When both tangent and cotangent are defined, they're reciprocals of each other. But If x is 0, that's going to make cotangent 0, but tangent undefined. And I can't take the reciprocal of undefined. So cotangent is the reciprocal of tangent if both are defined, but if tangent is undefined, cotangent will be 0. And of course, this is the same whether I'm working with a general circle or the unit circle, because there are no radii that show up in the formulas. So these are formulas that you should have a good working knowledge of, but I really like the ability to draw the picture here so that if I don't have them memorized, I can very quickly get them from my right triangle definitions.